The position of the shoreline over the time is highly variable as the tides create fluctuation in the level of the sea, moving the shore in and out, sometimes over hundreds of meters per day. Not just the level of the ocean that influence the shape and topography of the shore. The material that makes up the land, soil and rocks is constantly flux due to the scoring by seawater. Generally, coastal erosion is the loss of displacement of land or the long-term removal of sediment and rock along the shoreline due to the action of waves, currents, tides, wind-driven water, or other impact. Besides that, human activities such as sand dredging and harbor construction have been disrupting the continuity of sediment transport and in turn accelerating coastline erosion. One of the case studies is the WALLOPS Flight Facilities Emergency Shoreline Stabilization Projects. The WALLOPS Island is a 6 square miles island in Accomack Country, Virginia, part of the Virginia Barrier Island that stretches along the eastern seaboard of the United States of America. WALLOPS Flight Facility is a rocket launch site on WALLOPS Island and currently experiencing beach erosion of 10 to 22 feet a year. Some access roads and parking lots have to rebuild several times due to shoreline erosion. In order to overcome this problem, geotextile tube as geosynthetic material will be used.
The Drainage Department of Irrigation and USACE manual draws out that a functional design of geotextile tube as a breakwater for erosion control must fulfill three main criteria. Firstly, structural integrity, whereby the geotextile tube must have the ability to withstand the effect of extreme storms without itself suffering significant damages. Hence, wind and waves record must be observed in order to determine the dimension of geotextile tube. Second, functional performance, which is to deal with the effectiveness of the structure at its intended function. For the case of WALLOPS Island, the function of geotube is to break water, but act as a barrier to protect the coast from the forces of wave. And lastly, constructability, which relates to means, methods, materials involved in the construction. To fulfill the above stated standards and guidelines, the material of the geotextile tube have to undergo several testing to prove its reliability in terms of nominal tensile strength, elongation at nominal strength, static puncture resistance, factory seam strength, apparent opening size, and UV resistant retain strength. By fulfilling all, could result in a satisfactory design that encompasses safety, efficiency, reliability, cost effectiveness, with the consideration of both environmental and social aspects.
This is the proposed design of geotube. As well can see, this is a drawing sketch of geotextile tube. In this case study, the design team gathered some information to design this geotextile tube. Firstly, the water level is 2.2 meters above the ground surface. For this erosion control project, engineers decided to use the 10.4 meter circumference size of geotextile tube with 4.2 meters wide and 1.8 meter height. Other than that, the geotextile tube is binded together with geotextile scroll apron on both sides by spanning 8.2 meters out due to stability consideration. At the end of the scroll apron will attach with anchor tube. Therefore, the scroll apron will be act as the foundation of the geotextile tube to ensure the geotube will lock in place over long service period. Stability checking is essential, especially for the retaining structure like geotube. Stability checking consists of sliding, overturning, and bearing capacity. For the stability checking of the geotextile tube, the calculation is almost similar to the typical retaining structure such as retaining wall. Therefore, the stability checking for this geotextile tube is achieved satisfaction with enough safety factor of sliding, overturning, and bearing capacity. This is an engineering drawing of the GeoTextile tube. All the details of the GeoTextile tube is stated in this drawing.
The next one will be the implementations and considerations of the installations of GeoTextile tube at WALLOPS Islands. In this project, there are two slurry pits. The first one is located at the north end of the project site, while the second one is located at the midway between the project area. So, all between these both slurry pits, there are stockpile of sand beside it. So the first slurry pit is around 3,800 meter cube, while the second one is 7,300 meter cube, while the second one is mostly covered for the pumping requirement. So in this project, there are two types of pump is used. An abrasion resistant submersible pump with agitators and the hydraulic drive of 75 horsepower, and it was hung in the middle of the air above the slurry pit. And then another two 6-inch and 8-inch self-priming trash pump were used to supply the seawater to the pit. Both the pumps supply the water at a rate of about 1,700 gallons per minute. After that, around 10 to 15% of the solid slurry is transferred through the piping system with constant adding of the sand and the water supply rate. And then in this piping system, there is a mechanical pinch valve which is used to control the flow at each fill port. And then the dynamic adjustment is required for the pump speed, slurry storage percentage, and number of fill ports throughout the project development. This is because piping system is changed in terms of the pipe length or the structural combination as the project carry out from north to south. So there are three considerations of implementation in this project. The first one, the time constraint, the pumping demand, and then the safe and clean working environment. The time constraint will be the most significant one because the poor weather conditions along the shore of the WALLOPS Islands, such as the low tide or the storm, will affect the water supply for the slurry pit. This will cause numerous delays to the project, and so that the construction duration is limited.
Benefits of geotextile tube over conventional engineering method. One of the conventional engineering methods for breakwater is a rubble mound breakwater. It is commonly seen in European countries, which are made of small stones like 6-4 and larger stones as the armoring layer. Rubble mound breakwater creates sheltered areas and are able to keep most of its function despite some of the armoring layers being removed by the sea waves action. However, remedial work through time to fill the voids and provide additional stones to the lost layers or damaged surfaces must be replaced to ensure continuity of the functionality. The cost of rubble mound breakwater increases with depth of sea. Caisson breakwater is another commonly seen erosion control methods in countries such as Japan and Korea, where large boulders are difficult to obtain but in abundance of cement supply. Caisson breakwater is a form of vertical breakwaters with infills to resist overturning from the wave force acting on the structure. However, the structure is expensive for shallow water, hence commonly seen in deep water. The vertical breakwater needs to be properly designed and upgraded over reinforcement maintenance to function through time. The construction is complicated and needs special skills and equipment. Due to its stochastic properties in loads and resistance, comprehending the failure phenomena of the vertical breakwater is also complicated. Geotextile tube, or also known as geotube, is a leading alternative in protecting the shoreline. Unlike conventional materials, geotextile tube size can be customized according to the project requirement, increases the popularity and worth of the material. Geotube in this particular study can simultaneously serve as breakwater as well as re-nourishment of the beach ecosystem through the increase in sand deposition after application. Made up of several parts consisting of the core material, armoring layer, filtering layer, and scour protection, allows water to flow through the pores while retaining the infill sand without causing the geotube to move from its designated position, acting as breakwater to prevent further erosion of the shoreline. The implementation took only 2 months, requiring only 6 crew members to complete. There was little to no future maintenance requirement after installation of the material. This efficiency is unlikely to be seen in conventional hard coastal structures for erosion control. Aside from low consumption of time and construction costs, implementation of geosynthetic technology only requires simple equipment and low-skilled workers as compared to rock revetments and steel seawall.
So there are several recommendations for the utilization of geotextile tube. The first one is use ultraviolet stabilizer such as carbon black in the geotextile tube. Second, we can select high-strength woven polypropylene geotextile. And last but not least, we can increase the number of layers of geotextile in the geotextile tube. In a nutshell, after the completion of the project, it significantly have the sand deposition along the entire length of project. And based on the result, it proved that the geotextile tube prevent further erosion and also encourage renourishment of the beach ecosystem. To obtain more stabilization and improve the safety factor of geotextile tube, we can fill the area behind with sand and plant grass.